Okay, thank you. And I would like to thank the organizers for inviting me here. This is my first time in UCLA, and I enjoy it a lot. And yeah, so when I came to the conference, I started realizing that I might be the first talk that presents something that is not twisted and not graphene and not anything like that, and not even really 2D. It's a 2D interface between 3D materials. So I started getting really worried. Then in the talk earlier today, it got a little better because it seems that it also didn't contain the themes. And then at the very end, it was twisted. So unfortunately, I'm going to be the first probably to present something which is not twisted, but I think still is, hopefully will be, you find it interesting. So this has to do with oxide interfaces, and I will introduce them a little bit in more detail so that everyone will be on the same page. And I will also present experimental work of my colleagues, the group of Yoram Dagan at Tel Aviv University. Basically, he got me interested in those materials ever since coming to Tel Aviv 6 years ago. And especially in these projects were involved his former students Eran Alon and his former postdoc Prasanna. And in the theory, it was me, and in the last part, my former postdoc Udit, and published in those papers. So, okay, so before I get into that, maybe let me mention some other things that our group has been doing and are related to some things mentioned during this conference. So I will not talk about them, but if people are interested, I will be happy to discuss them during the breaks. So one thing we have been interested in is using dissipation, which you usually think of as something that destroys quantum coherence and destroys interesting effects. So using it to induce many-body correlated states, and especially many-body quantum coherent states, which are topological. And the reason I mentioned it here is because it turns out that flat bands play a very important role in that, so that connects that to things discussed during the week. Another type of systems we are interested in are its hydrodynamics of electrons, and in particular Hall viscosity, the viscosity analog of Hall conductivity. And in recent works, we looked at how it affects edge magnetoplasmons. And also we found that Hall viscosity, it's generally a symmetry protected topological index in gap systems, but somehow it's pretty robust to disorder, although it shouldn't have been. And another topic is two-dimensional topological insulators and magnetic impurities. So those are not the topics of the talks, but again, if people are interested, we could discuss later. So to get into the topic of the talk, some more general introduction of 3D crystal interfaces. We heard a lot about 2D interfaces, but let's go 3D. So the most well-known ones are maybe semiconductor heterostructures, which are very nice, give us devices where we can control the flow of electrons, build interferometers, quantum dots, whatnot. They are very nice, but in some sense they are a bit boring because the physics is in many ways a weak interaction physics. To get really strong interactions, you need to go to maybe high magnetic fields and have quantum Hall. But apart from that, it's not so exciting physics in many ways. Now, it can get more exciting if you have topological materials. Those are also usually some kind of semiconductors or semimetals. But in terms of actually doing transport, they are not. Most of them are not that good these days. So other materials could be interesting. And here come the oxides. So I'm going to discuss interfaces between oxides. And the interesting thing about them is that those materials, actually, I'm going to discuss about a family of materials. And as you change some parameters, you could have many interesting correlated phenomena. You can have orbital order, charge order, ferroelectricity. You can have all kinds of lattice effects, magnetism, superconductivity, etc., etc. And especially when you build interface, you can take different oxides with different properties and put them together and hope to get something interesting and also controllable. So just As an example, going a little bit out of this line, if you take an oxide like strontium titanate and grow on it materials like ferrum selenide or nickelate, so actually you find that the superconductivity that you expect to get in those materials is somehow very much enhanced when you grow a single layer or a few layers on those oxides. So this is one interesting thing, but what I'm going to concentrate more on is when you put two oxides on top of each other, and then you can imagine taking two oxides with different properties, putting them on top of each other, and maybe have an interesting interface. Now, the basis of most of those things is strontium titanate. Many of those interfaces are based on that because this is a good material to grow, so you can buy nice crystals and then put some other things on top of it. So let me explain a little more about the basic physics of strontium titanate, which will be important for what is going to go later on when we put an interface on top of it. So this is the material. It's what is called perovskite, and so we have the strontium at it's a cubic crystal, strontium at the corners, titanium at the center, and we have this octahedra of oxygen surrounding the titanium. And this is again the structure here. And now, if we look at it, it can have different, we can look at the phonons or different things that the lattice can be distorted in. So one thing that could happen is that the titanium will shift, and this would actually create, because titanium is charged in this lattice, so this is going to get to create an electric dipole moment. So this would make the material ferroelectric, and it turns out that this material is almost a ferroelectric. As you decrease the temperature, the dielectric constant rises to about something like 20,000, but it doesn't diverge, so it doesn't become ferroelectric, but it's a quantum power electric very close to some ferroelectric critical point, which you can reach by doping and other means. Another thing that happens to this material is this thing. So as you lower the temperature below 105, there is a slight tetragonal distortion. The octahedra in adjacent cells, they rotate, and from cubic, the symmetry is actually reduced to tetragonal. This is not going to be so important in what's going to go on, but still it's good to keep in mind. Now, in terms of electronic properties, so undoped strontium titanate is an insulator, but when you dope it, things start happening, and the orbitals in which things start happening are the titanium 3D orbitals, which in the crystal field, they split into T2G and EG, and the EG go upper in energy, so they are not important, but the T2G, they basically form the conduction band, and when you dope, those are going to play the important role. And because of their structure, so each one of them has, just because of considerations of the overlaps of nearest neighbors, so let's say the XY would give rise to a band which has a low mass, high mobility in the X and Y plane, and high mass in the Z plane, and similar things for the other orbitals. Again, this is going to be important soon. Now, when you dope it, it not only becomes a conductor with these orbitals, it actually becomes a superconductor. And this is a very peculiar superconductor. As function of the doping, actually the critical temperature is non-monotonic. It increases and decreases as function of doping. And also it's unusual in many other ways, because the carrier density can be below 10 to the 17 per centimeter to the third, and still it becomes a superconductor. It's one of the most dilute superconductors known. And the unusual thing is that the Fermi energy is very low at those concentrations, and it's much smaller than typical phonon frequencies. So this is well outside the usual BCS limit. In that sense, it could be similar to things discussed in bilayer graphene and other systems. And there is actually a big ongoing debate about what's making that superconductor. So people have suggested that maybe it's a soft ferroelectric transverse optical phonon. So the material is almost a ferroelectric. So there is some phonon mode which is becoming very soft, so maybe that is the glue for superconductivity. People have also suggested longitudinal optical phonons, or maybe purely electronic plasmons. And there is a big debate, because for all of those things, if you try to estimate the coupling constant, it tends to be too small. Or another problem is that because you are outside the usual limit, then the usual theoretical tools, the Liashberg theory, do not apply. And maybe, I mean, I personally believe that maybe some combination of this is responsible, but this is still debated. And a nice unbiased review is this recent review, where you can read more about it. So this is STO. But now, okay, we want an interface, right? We want to talk about something 2D in this conference. So let's take STO and grow on it another similar material from the same family, but lanthanum aluminate. And I will be discussing first the 001, meaning that we do everything along the z-axis. Okay, so this is actually an example of something grown in the lab at Tel Aviv. So this is the STO substrate, and this is, I think, 8 layers of LAO grown on it. And when you go, you can actually follow the diffraction pattern with, and basically grow how many layers you want of LAO on top of the STO. And now, okay. And now, in this seminal paper by Harold Wang, something like 15 years ago, they have shown that when you do this growth, then if the STO, when you look at it, it's composed of titanium O2 layers and strontium O layers. So if it's terminated by strontium O, and then you grow the lanthanum aluminate on top of it, then you grow an insulator on top of an insulator. You need to be careful not to dope the material, but you can do that while growing. So you grow an insulator, and it keeps insulating. That's okay. But somehow, if it's titanium O2 terminated, then you grow an insulator on an insulator, and it starts becoming conducting. So it's 2 insulators. They are not doped. They are not topological, so it's not some topological edge modes. Yet you get conduction. And it turns out that you need a minimal number of 4 unit cells to get conduction, 4 unit cells of lanthanum aluminate. And what is the reason for that? So people believe that the reason is actually basically very simple. It is what is known as the polar catastrophe. And the idea is as follows, that if you look at the charges of the strontium, titanium, etc. in the presence of oxygen, it turns out that in strontium titanate, the different layers are electrically neutral, whereas in lanthanum aluminate, the different layers are actually charged by plus and minus. So if you have those layers, plus, minus, plus, minus, plus, minus, it's like a series of capacitors. You have electric field which is finite and zero, and then the potential accumulates from layer to layer. It's like capacitors in series. And this can definitely not go on, because eventually you'll create a big potential difference between the 2 sides, which will become bigger than the band gap. And the first thing to break is basically strontium titanate. So what is going to happen is that if you have enough layers, and the number is indeed roughly 4, then you are going to create a very big potential difference. And then it's going to be bigger than the band gap of the strontium titanate. And then what the system is going to do is to move electrons from basically the top layer here into the interface, and go actually into the titanium orbitals, because this is the conduction band. And then if you put here a layer with charge minus half density as compared to the other layers, then you see that the electric field will oscillate up and down, and the potential will not accumulate, so the system will be happy. So ideally, the system should transfer 1/2 of an electron per unit cell, which corresponds to a density of 10 to the 13. Now, when you measure transport, you see that the system indeed becomes conducting, but actually the number of carriers that you see that are mobile is way less than that. And this is a bit of equation to which there is no good answer, but it's accepted that most of the carriers are trapped somehow, and only few of them actually go to the right bands to take part in the conductivity. We'll see that. And then you can do something more sophisticated ab initio, and this also shows you that when you have enough layers, 4 or 5 of LAO on top of STO, you close the gap basically and get conduction at your Fermi energy. Okay, there are other things that could contribute to that, but they are not important. Let me skip this. Okay, and then, so I told you that this is interesting because like semiconductor heterostructures, you can, basically it's a 2D conducting layers, and then you can put some gate on top or on the bottom and use electric field to control the electron density, and all the properties of this interface can be controlled continuously, not by changing composition, but by applying gate. So you can control the conductivity in situ and think about devices. You can do more fancy things. So this is done especially by the Pittsburgh group of Levin. So what they do is they create LAO with fewer layers than what we need for conduction, and then use a conducting AFM to write, let's say, a wire of LAO, and to make the system conducting just on a wire, and in this way build all kinds of interesting devices. Or another thing that you can do, and this was done at Tel Aviv, it turns out that if you have basically a modulation, you go in some regions 3 unit cells of LAO, in some regions 1 unit cell, so each one of them is not conducting, but somehow the 1D interface between them actually does become conducting. Not only it becomes conducting, but at least in some of the devices, you see as function of gate nice conduction steps as function of a gate. And this is pretty surprising that you see those nice conduction steps, because this is a few microns long, and the material is not extremely clean or high mobility, so you would expect backscattering. And another surprising thing is that the steps are in units of 1 e²/h, not 2. So maybe spin is somehow broken. So this is still not yet understood, but maybe people in the crowd will get interested. In any case, those are published results by my colleagues. And okay, so this is not what I'm going to discuss. I'm going to discuss some other things. So let's try to, okay, so LAO and STO, 2 insulators, the interface becomes conducting. And now let's see that it's more complicated than it seems at first sight. So first of all, let me tell you about the things that are probably not so important. So people have looked into magnetism in this interface, and various things that look like there is some magnetism, but when you do local probe measurements like those ones, and also when you do muon scattering, it seems that there are some permanent magnetic moments, but they are somehow dilutely scattered everywhere. So it's not yet so clear what they are, but it appears that there is some local magnetism, although because it's local, when you do 2D transport, it doesn't affect you so much. For example, you see an isotropic magnetoresistance, but you don't see any hysteresis. You start seeing those things when you go to those 1D systems that I mentioned, and then it's clear that even if along the 1D there is just one magnetic region like that, you will be sensitive to it, but somehow in 2D you are less sensitive to it. So I'm going to forget about magnetism in the following. Another thing that I'm going to forget about is that I told you that there is this tetragonal distortion below 105K, and actually you can have different domains where this tetragonal distortion can be along X, Y, or Z. And if you have a big sample, and again this is a scanning probe, you see that actually conduction is enhanced along the domain walls and maybe even superconductivity, but the samples I'm going to tell you about are going to be smaller than that, basically smaller than the typical domain, and we have evidence that they're basically single domains, so domain wall physics is interesting but not going to be important to us. Okay, so I told you that the interface is, what is important? So the interface is becoming conducting, it also actually becomes superconducting. And not only it becomes superconducting, but as function of gate, you can have a negative gate, which basically depletes the system. And then the TC goes to 0, although actually it goes to 0 while you still see some conductivity. So you don't need to fully deplete to see 0 TC. And then it increases, which is OK, and then it decreases. So we have a dome, and this is unusual. It's very far away from, you know, some integer filling or something like that would be like here at inaccessible regime. We are only filling the bottom of the bands. So something like that is unusual, and people started immediately thinking about relation to high TC and other more fancy stuff. Okay, so this needs to be understood. And my colleagues have also seen that. Let me skip this. And as I told you, there is also superconducting dome if you dope bulk STO. And you could ask whether or not those are the same. And let me point out that here it's plotted as function of doping, so as function of carrier density. Here it's actually plotted as function of gate voltage, and usually associate gate voltage with carrier density. But as I will show you, actually this is not so simple. So this comparison is not as simple as one might expect. And okay, to understand more, you need to do some more sophisticated measurements. So my colleagues have done, other groups as well have done Shubnikov-de Haas measurements, so magnetic oscillations, and also low field Hall. And usually if you have a single parabolic band, then the Hall resistance, you can get from it a Hall number, which is some proxy of the electron density. So again, for a single parabolic band, it would be the electron density. So if you just calculate this quantity, you get things of the order of 10 to the 13 in terms of density. On the other hand, if you look at your Shubnikov-de Haas and translate the period of the oscillations into density, you get a very different number. It's not, okay, it's not given here, but it's of the order of 10 to the 12th. So there is some disagreement between Shubnikov-de Haas and Hall, and we need to understand that. Now, the system is not as simple. I mentioned that there is more than one band, so we need to be cautious when interpreting that. And also, if you do more sophisticated measurements like NEST, you see that the two bands are important, but still we need to understand. So we basically needed to understand, that was the situation before we started the works that I mentioned in the beginning. So why is superconductivity suppressed on the overdubbed side? Is it related or not to what is happening in bulk STO? Which band is responsible for superconductivity? And why do we have this almost order of magnitude disagreement between densities that we extract from Shubnikov-de Haas and from Hall? And the solution to solve all that, and this was the thing that my colleagues did the first time, is to measure all those properties, Shubnikov-de Haas, Hall, and superconductivity, in the same sample and as function of gate. So to change the gate and to see how all those things change. So first of all, this is superconductivity in a sample as function of gate. This is not so new, although you could notice that the scale here of the gate is small. It's only a few volts as opposed to the 100 volts in other experiments, and this is due to a clever design of the geometry of the sample, that you can use very low gates, and that's important in order to be able to do all the other measurements without destroying your device. So they see also the superconducting dome. And now you can plot the superconducting transition temperature, or in this plot, it's the critical field as function of the gate. And together I plot also the inverse Hall coefficient in units of density. And we see that they are actually both non-monotonic, and they have peak at roughly the same value. But this is still not telling you enough, because superconductivity is a complicated property, and actually Hall number is also pretty complicated when you have more than one band and when the dispersion is not parabolic. So they reconcile, but what does that teach us? So to have something definite, we need to go to high fields and measure Shubnikov-de Haas. So basically, this is the conductance as function of, or the resistance as resistivity as function of magnetic field up to very high fields. And it looks almost linear, but then when you subtract the linear background, you see some oscillations. Those are Shubnikov-de Haas oscillations, and you can extract their frequency and look at it as function of gate. And you can barely see them, but they are enough to analyze. And I apologize, they are not plotted in units of density, but in units of frequency. I will tell about density, but what you immediately see is that Shubnikov-de Haas is also non-monotonic as function of gate. And now this is really striking. Why is it striking? Because Shubnikov-de Haas frequency tells you about the area enclosed by the basically by your Fermi line. And since this is 2D, not a 3D material, but a 2D material, then basically it gives you the area of your Fermi area, and this is exactly should be the carrier density of the band that you are probing. So in 2D, Shubnikov-de Haas frequency should be density. And then it's actually very peculiar to see this density being non-monotonic as function of gate, because as we increase gate, electrostatics tells us that total density should be increasing. But we see that it's non-monotonic. And also when you translate that into density, it's again about an order of magnitude, or at least a factor of 5 smaller than what you extract from Hall, although they peak at the same point. So we need to explain that. What can cause this behavior? So the first thing that comes to mind, and this is also what Refer suggested to us, is that maybe carrier density is not monotonic as function of gate, and maybe this has something to do with the nonlinear dielectric characteristics of STO at high fields. But then you remember that from electrostatics or thermodynamics, if you basically increase gate, you are going to increase density, maybe in a complicated fashion, but increase. So you cannot increase voltage on a capacitor and decharge it. So this is excluded. But what could happen is the following. So our idea was that the following, that you might have more than one band, and that it could be that the total density is monotonic, but the distribution of the density between the two bands is not monotonic, and this is what causes this behavior. So let me explain that. And let me start with a simple example, first of all, of how things like that could happen, and then how they could explain what my colleagues are seeing in the experiment. So this is a simple cartoon picture of the things that could happen. So assume that we have some two bands in a system as function of energy, and one of them has high mass, so high density of states, it's narrow, and the other one has low mass, so low density of states. And I will plot here as function of gate the occupancies, and one would be completely occupied. So then, if I increase the gate voltage, I pull the bands down, and when they cross the Fermi energy, this is a cartoon of what is actually happening in the system, I start filling in the lower band, and if there is an interaction, when I fill in the lower band, I actually increase the energy of the second one, but eventually I will start charging it as well. So this is the usual picture. I charge one band, I charge the other, and everything is monotonic and nice. What would happen if the bands overlap? So the low mass band has such a low mass that actually it has a density of states which overlaps with that of the band with high mass. Then it could be more interesting. So to see that, suppose I start increasing gate voltage. I start putting in actually particles into band 2, because it has this tail in the density of states. As I do so, I increase the energy of band 1, so it increases in energy. And okay, so I get something like that. This is filled, this remains empty. Now let's say that I start from the other limit. Suppose I went to extremely high gate voltage, I filled in both bands, and now I start decreasing the gate voltage and start emptying them. So the first band to get depopulated is again band number 2, again because it has this tail in density of states. So this is what I'm going to have on this side. And the only way to reconcile those two limits is that somewhere in the middle, I started filling in band number 2, then I regretted, then I filled in band number 1 and took the electrons out of band number 2, and then filled band number 2 again. So the total density is monotonic. I haven't broken that, but the distribution between the bands is not monotonic. So we believe that this is the basis, based on the Shubnikov-de Haas, this is the basis of what is happening in our system. Just that in our system, it's a bit more complicated version of that. And the reason is that we don't have bands, just one band with always high mass and one band with lower mass. They are more complicated, and the density of states are changing as function of the Fermi energy. So we needed to do a better modeling. So as I told you, what are going to play a role are those T2G orbitals. And in the bulk, they are degenerate, and there are some couplings that break this degeneracy. And when you have this interface, then you basically have confinement. And then if the confinement is in the z direction, the xy band, which has higher mass in the z, the confinement direction, will be lower in energy, and the other bands are going to be higher in energy. So your first band is going to be xy, and it's going to have actually low mass in the direction of xy, so in the propagation directions, and then will come the other bands which have high mass in z, but they have low mass in z, but actually they will have higher mass along the other directions. And then, so this is a typical picture. First you have the xy with low mass in the xy, and it's lower in energy at the interface, and then the other bands which have high mass, higher density of states. But the bands are mixed and coupled by different things, and then it becomes a bit more complicated. So we need to take that into account. So we basically write down a model based on those earlier works, which are themselves some tight binding modeling of ab initio data and also of experimental results. So this is going to be our Hamiltonian. I'm going to write the different terms. So there is the tight binding part. It has many terms, but most of them are not actually important for the physics. The main thing is this diagonal part. So the basis is xy, xz, yz cross spin up and down. So there is the part which is spin independent, and it encodes the different mass or the different hopping element along different directions. So there is a large and a small one, and there is a factor of 20 almost between them. And also there is this delta E. Because of the confinement, the xy is going to be lower in energy. And on top of that, we need to add atomic spin orbit. This is actually very important for mixing and splitting of the bands. There is also Rashba, but it turns out to be quantitatively less important, but we can take it into account. And then we need to take into account interactions. And our model for interaction is going to be a local Hubbard U. And the justification for that is that because we have such high dielectric constant in the STO, 20,000, then the long-range part of the Coulomb is going to be much suppressed by this dielectric constant. So it's not going to play an important role, at least not for the effect I'm discussing. So the short-range part is the important thing. And then if you use symmetry, you find that, OK, if you do Hartree-Fock, you basically have only 4 Hartree-Fock parameters, so way simpler than bilayer, twisted bilayer graphene. And again, we can take all those numbers and also the Hubbard U from DFT and experiment data. So we didn't want to use them as fitting parameters, otherwise you have too many parameters. We just try to take reasonable numbers from the literature. And then you take that and you look at the bands. And what you find is that, OK, first of all, this is a general thing. The last band starts with low mass, then it becomes high mass because they mix. And the second band starts high mass and then becomes low mass. And then what is going to happen is that as you start filling in and increasing Fermi energy, you first filling this one, then you start filling in the second one, and here it has high mass, so you actually like to fill it in, and you keep filling it in. As you increase the Fermi energy, this becomes actually low mass, and then because of the competition, you actually regret filling it. You take the electrons out of it and put them in band number 1, which has a higher mass. So this is a more complicated version of the simple story I was showing you with cartoons before. So what you get out of that is that you have 2 bands. Band number 1 has monotonic population. Overall population is monotonic, but band number 2 is non-monotonic. You populate it and then you regret and put things into band 1. You also notice that the population of band 1 is high, about 10 to the 13, like the numbers we get from Hall. The population of band 2 is small, around 10 to the 12. This is the Shubnikov-de Haas numbers. So our interpretation is that band number 2 is basically, when you think about it, it's a bit further removed from the interface. So it might have less scattering, higher mobility. In Shubnikov-de Haas, you barely get Shubnikov-de Haas. So you only see the mobile band, which is band number 2. And this is why you see there's something which is non-monotonic and also on on this scale. In Hall, you see some combination of both of them. So you see a big number, but still because this non-monotonic thing is involved and has a high mobility, then actually your Hall is going to be non-monotonic. So if you put the numbers of carrier density and you compare that to what you get from Shubnikov-de Haas, you get basically the same thing up to a factor of 2. And again, we didn't try to optimize the parameters. We just used parameters from the literature. If we played with them, we could fit anything to anything. But even using those bare parameters, we get the same behavior in the experiment up to some factor of 2. And then, okay, so this basically nicely explains both superconductivity and, this explains what we get in Hall and what we get in Shubnikov-de Haas. What about superconductivity? So superconductivity is definitely much more complicated. And as I told you, there are many debates in bulk STO, and some of this carries over to this interface system.
Can I?
Yes?
Why should you see the second band in Shubnikov-de Haas?
Yes, so we believe that it has higher mobility because it's further from the interface, and in Shubnikov, even elastic scattering suppresses Shubnikov. So, and they barely see Shubnikov. So basically our assumption is that band number 1 has a lower mobility, and then it's below what they can see, and band number 2 has higher mobility, and they see only that. In any case, they don't see 2 frequencies, although it's kind of clear that 2 bands are playing a role there. So they only see the more mobile band, and there are reasons to believe that this is the upper one, and it definitely gives a consistent picture.
More mobile because of where it is in space, not
yes.
because of its mass.
Yes.
Yeah. 5 minutes.
Okay. Good. No, it's actually good. So a good point. And now, what about superconductivity? So superconductivity is complicated, and we didn't attempt to do full modeling. Again, it's also debated what's causing that. But we said, okay, let's do the following exercise just for the sake of exercise. We had those SrTiO3 calculations. We have a density of states. Let's assume that the second band is more mobile, so superconductivity is capping only from that. Of course, you can argue against that, and I'm not claiming that this is the thing that's happening, but let's, for the sake of the argument, say that superconductivity is coming from band number 2, and let's be so simplistic as to use weak coupling BCS, which is also not correct, but just for the sake of the exercise. And then take a coefficient like at the Debye temperature and whatever, and basically put here, we have the density of states, put this number, the decoupling strength, so that the maximal TC will be the number observed in the experiment. And just because of the non-monotonicity of the population of the second band, and therefore also the density of states, you immediately get a dome structure which is not too far removed from what they see in the experiment. So it's not to claim that we have explained superconductivity, but rather to claim the opposite, that basically the non-monotonicity in occupation of one of the bands that you see in Shubnikov is definitely enough to explain what you to account for what you see in superconductivity. If someone comes and claims that the dome in superconductivity is more fancy physics, then they need to give another proof, because the non-monotonicity that you see in Shubnikov is enough to explain what you see in superconductivity. And this is what I stressed before, the comparison with bulk STO. In bulk STO, you had the dome as function of filling, and actually here you have a dome as function of chemical potential or a Fermi energy, and this is not the same because the density, at least of one of the bands, is non-monotonic as function of that. So there is a different mechanism in play here. And okay, this is a summary of all those things I was telling you. And now very briefly in the 4 minutes I have left. So you could say, okay, this is a nice theory that accounts for the observation at 100. Is it correct or not? Maybe there is something else explaining all those things. So the idea was to try and test what would happen in a different interface, because then some of the elements in this explanation are not going to be the same, and the physics is going to change, and whether or not that is going to fit the same kind of theory. So my colleagues are also able to make the 1-1-1 interface. Somehow this is harder to do, so not many groups can do that. So that just means that you cut STO along the 1, 1, 1 direction in this way, and you grow LAO in this way. And then actually, when you look at it, it's a cubic crystal, but you cut along this direction, you have hexagonal symmetry. So I guess at least here I connected a little bit to the graphene that we have seen throughout the conference. But in any case, okay, you need a bit some more work in your Hartree fork, because actually you need to include at least 3 layers before things repeat themselves in this direction. So you have many more orbitals. Basically, you have 18 by 18 Hamiltonian instead of 6 by 6, but still much easier than twisted bilayer. So in any case, you have this 6-fold structure, and actually you see that in magnetotransport you see a 6-fold symmetry in AMR, but this is not the important thing here. So the important thing is that when you look at the 2G orbitals and you put them at the interface, now they don't split as XY versus YZ and XZ, but they split as A1G and EG prime. And those are much more symmetric combinations of the orbitals. And in particular, actually the order between them is not determined by the confinement. They basically have almost the same mass. The order between them is some secondary effects, which we took from DFT, and because the masses are quite the same, so this non-monotonicity of density of one of the bands should not happen here. So if we perform a measurement, we should expect to see here different things. And this is my colleagues did. So they went and did the same kind of measurements on 111. And what they found is that this is Shubnikov. Shubnikov is still, and this is Hall density, this is Shubnikov density. There is still this big difference between them, but now Shubnikov is monotonic. Hall is not monotonic, it has a peak here. It's very different scale. When you look at TC, it also has a peak. The peak is TC is very far removed from the peak in Hall. So they both have peaks, but they are not correlated as used to be the case in 100. So this is different. And when we come to the theory, actually all those things are very natural. Because when we look at the bands, now the bands have quite similar masses. They are different, but not very different. And therefore, indeed, when you do the calculation with basically the same parameters as we used for 100, you find that both bands have monotonic population. And this is why Shubnikov-de Haas now is monotonic. It again seems to be probing band number 2, but it's monotonic. So this roughly corresponds to what we have seen in Shubnikov. As for the Hall, we see something which is non-monotonic, but this is actually happening before we start feeling band 2, right? We see that in Shubnikov. This peak is happening before we start feeling band 2 and seeing things in Shubnikov. And the reason could be simple because of the 6-fold symmetry along this interface. So the Fermi surfaces of band 1 are very much curved, and this curvature, it means that it has mixed electron and Hall features, and this is enough to give rise to enhanced Hall number in some regions of the Fermi energy, and which are like in the experiment. Now, as for TC, well, again, it seems that superconductivity is somehow in the region where band 2 is important, and here we are less certain. Again, we did the same trick of just plugging in the density of states of band number 2 into the BCS formula, and somehow it does give you some pretty shallow dome, because density of states is not exactly monotonic, but here again the density is monotonic. TC is not monotonic. It could be just because of variation of density of states. It could be other effects like in bulk STO, but in any case, it's not because of things going between the bands as in 100, because this is not happening. And indeed, the peak in TC is not correlated with anything in Shubnikov where there is no peak, and in anything in Hall where the peak is at a different place. So to conclude, we have seen studies of 001 and 111 LAO STO. In the first one of them, all properties that were measured were non-monotonic with peak at the same place. In 111, Shubnikov is monotonic, the others are not monotonic but not correlated. And if you invoke a simple model of bands which compete among themselves because of repulsion, you can fill one but maybe not the other, then actually it nicely accounts for what happens in the two materials. In this one, there is a big difference in effective masses, so population is transferring between the bands, causing non-monotonicity in all quantities. In this material, it is not happening, so Shubnikov is monotonic. Other properties are not, but this is due to particular reasons, not because of this effect. And now there are many interesting things that one could look into in the future. So it would be interesting to do full ab initio, not just Hartree-Fock, and see whether one can get all those effects. I believe that yes, but it's, from what I understand, it's a bit hard technically to change gate voltage in DFT calculations, but hopefully someone will try that out. And then fundamentally more interesting things are to understand better the superconductivity and to see whether mechanisms that have been proposed can be incorporated into this picture successfully. And another thing that my colleagues are doing is calcium doping the STO. This should make the system ferroelectric. So if superconductivity is enhanced by ferroelectric fluctuations, then this could enhance superconductivity. They start seeing some complicated results, and hopefully we'll have something to report about that soon. So thank you for your attention.